In section 11.5, we're going to talk about Charles' law. Charles' law relates volume and temperature. So there's a picture there of a hot air balloon. Now we have personal experience with helium balloons, right? And helium balloons float because helium is less dense than air. Why does a hot air balloon rise? Pardon me? Hot air rises, yeah. Why does hot air is less dense than cold air? Okay, because when you heat the air, you change its density because you're changing its volume. So heating a gas increases the volume if the pressure is constant. And in a hot air balloon, the pressure is going to be constant inside and out because it's open at the bottom, right? This is open down here. The mass isn't changing. The mass of the particles is the same, but they're expanding and getting bigger. And so there's more nothing in the gas, and so the density changes. The density decreases. Because density is mass divided by volume. If the volume gets bigger, but the mass is the same, you've got the same number divided by a larger number, then the quantity gets smaller, so the density decreases. And a lower density gas will float in a higher density gas just like a lower density liquid floats, like oil floats on water because it's less dense. So Charles did some experiments like this where he changed the temperature of the gas. So as we've learned in lab, the x-axis is the one you control, and the y-axis is the one that you measure. And so if you increase the temperature of a gas, its volume increases. Yes, and just ignore the thundering noises in the background. There's someone doing something on the roof. So the volume increases with the temperature. And it's always interesting to see where, this one obviously is making a straight line, isn't it? We've done some graphing, and we've seen that sometimes the lines are kind of curvy or they seem non-continuous, but this is forming a beautiful straight line. And it intercepts with a zero volume at minus 273 degrees Celsius. So would it be possible to have a negative volume? Does that seem like it would be possible? No. The smallest volume you could get would be nothing, right? And even that would be probably pretty hard to achieve. So the volume of the gas increases as the temperature goes up, and it decreases as the temperature goes down. And so if we extrapolate this line, we would predict that if you get to minus 273 degrees Celsius, which is really, really cold, that you would end up with a gas that has a volume of zero. So let's think about, kinetic molecular theory of gas. Think about a gas getting smaller and smaller, and because you're getting rid of the empty space, but eventually you're going to get it so close together that the particles are touching. And do the particles of the gas actually have some volume themselves? They do, right? It's really small, right? We had that illustration that in a liquid form, a can of soda, 12-ounce can of soda, if you turn that into a gas, it would fill up 1,700 cans of soda. So the gas particles are very small compared to the volume they occupy, but they do have some volume. So a negative volume is clearly impossible, and a zero volume is even kind of questionable. But if we extrapolate here, what they've done is they've taken this value of minus 273, and they call it absolute zero, because the theory is that you can't get colder than that. That is the coldest temperature that can be attained. So you think about, temperature and heat and cold and stuff, and, I never actually thought about it until just now. How cold could something get?
Until motion stops completely?
Yeah. The coldest you could get would be no motion, because temperature is a measure of kinetic energy, of motion of particles. And so, like we've said, in this desk, these solid particles, they don't seem to be moving, and yet they're vibrating, just like you guys are shifting in your seats, and you're moving a little bit. So absolute zero is where all motion of particles ceases.
Is that not even possible?
It has not been attained yet. There's people who try to get to absolute zero just because it's a thing that people say can't be done, so let's try to do it, right? Because that's the nature of humans, is there's always some people who want to do the impossible, which is good because that's how we learn new things. They've gotten really close. I think they've gotten less than 1 degree from zero, but nobody's actually gotten there yet. And, it's questionable whether you actually could get there. It's an interesting idea. But that's called absolute zero. And this is important for our class. So Charles, his initials were JAC. I don't remember what they stand for. JAC Charles. He was French and lived in the late 1700s, early 1800s. And he was the one who studied the relationship of volume and temperature in gases. And so the law relating them is named for him. And so Charles' law says that the volume of a gas and its temperature are directly proportional. This is only true if you use the Kelvin scale. And this is where the Kelvin scale came from. If we go back to this graph, what's the equation for a line? Just the general equation for a line.
Y equals mx plus b.
Y equals mx plus b. And so let's write that in here. Y equals mx plus b, where m is the slope and b is the intercept. So in order for y to be directly proportional to x, b has to be 0. We need to have no intercept. That makes for a much easier equation of a line. So what they said was, the Celsius scale is giving us a y-intercept that is not 0, and it's not working out very well. Let's just establish a new temperature scale for gases that'll give us a 0 y-intercept, and that's where the Kelvin scale came from. So when we deal with gases and calculations, we have to use the Kelvin temperature because the equations don't work with the Celsius temperature. And that's not true of a lot of other units, but it's true with the temperature conversions because temperature conversions involve addition. They don't just do multiplication and division, it involves addition. The Celsius scale plus 273 is the Kelvin scale. Okay, when you put those in, the conversions don't cancel out. Okay, so Charles' law, volume is directly proportional to temperature. This means that if you double the temperature of a gas in kelvins, you double its volume. Very, very important here.
Is volume in meters or is volume?
The volume can be in pretty much anything.
Oh, okay. That makes sense.
It's just the temperature. And I'll show you an example. Oh, wow, look. I kind of anticipated that. The equation of a line is y equals mx plus b. So we need to get the y-intercept to be 0 in order for this to work out. And we kind of already talked about the kinetic molecular theory of this. If the temperature of a gas sample is increased, the particles move faster. And if the pressure is going to remain the same, because we talked last time about how the pressure and the volume are related, if we've got the particles moving faster and the volume stays the same, the pressure is going to go up because they're going to be hitting more frequently. It's like, instead of people just walking around the room bumping into each other, now you've got people running around the room bumping into each other. And so the pressure would go up. In Charles' law, we look at constant pressure. So the volume must change. Here's an illustration. If you take a balloon, if you inflate a balloon and put it in an ice water bath and cool it down, it'll get smaller. And if you take that same balloon and put it in boiling water, it will get bigger. And this is something you can try at home if you're curious. But balloons will change size depending on the temperature. It's really kind of interesting. This is why if you go to a birthday party in the winter and you bring home some helium balloons and you leave them in the car overnight and it's cold, you go out the next morning and they're sitting on the floor, right? if you bring them inside where it's warm, they will revive and they'll start floating again. It only works like the first day, because after that, most of the enough helium's leaked out that they don't float anymore. But so there's an illustration of that. So we use Charles' law to calculate volumes and temperatures when those are the only two things changing. So here's the equation. Important that the pressure and amount of gas are constant. So those two things are not changing. All that's changing is volume and temperature. So V1 over T1 equals V2 over T2. That's Charles' law. And so, of course, we're going to do calculations. Here's an example. Sample of a gas has a volume of 2.80 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What was the initial temperature? And they want to know in kelvins and in degrees Celsius. You're like, okay. So what I showed you for Boyle's law is let's make a table and organize these numbers so we can keep them straight. So we'll read through the question again and just kind of write down these numbers as we come across them. So gas has a volume of 2.80 liters. So let's make a table over here. And so we've got 2.80 liters, and that's a volume. And so we'll call that condition 1 because we came across it first. At an unknown temperature. So we don't know what the temperature is. So there's a temperature involved here, but we don't know what it is. When the sample is submerged in ice water at 0 degrees. So we had this gas, and now we're putting it in ice water. That's the next condition. 0 degrees Celsius. When you're filling out the table, say, oh, wait a minute, that has to be in Kelvin, and convert it right away. So 0 degrees Celsius plus 273 is going to equal 273 Kelvin. Right? Okay. The volume decreases to 2.57. So this is condition 2, and now the volume is 2.57 liters. So we have our table, and we have one blank. There's a question mark in there. We're going to call that T2. We want to know, why would I call it T2? That's T1. Yeah. We're going to call it T1 because that's what it is. And we'd really be messed up if we didn't. Sorry. Okay, we got our table. So now we need an equation. So we've got temperature and volume. It did T over V, right? On the previous slide? V over T. It ends up being the same either way. So I just don't want to confuse anybody. V1, I've already done that. V1 over T1 equals V2 over T2. You know, if you can't laugh at yourself, who can you laugh at? Other people. So what are we solving for? T1. We're solving for T1. So I'm going to make, that's not a good color. So we're solving for this guy. He's in the denominator. This is where people do things that are far too creative with their algebra. Algebra is not a place to be creative. Algebra is a place to follow the rules. Okay, so some of you are very good with algebra, and so you just rearrange that equation and solve for T1 and you'll be good. And some of you are not so good with algebra, and so pay attention here. So what we're going to do, because fraction is the F word in school, we're going to get rid of the fractions. So we're going to cross multiply. And so we're going to take these two things and multiply them, and we're going to take these two things and cross multiply them.
The one that you did on Tuesday, you didn't do it that way, right?
Right, because there was no fraction.
Oh, okay.
Yeah. Yeah. So the initial equation for Boyle's law, P1V1 equals P2 V2. No fractions, so we're just good to start with. This one they always present in this fraction form. They have a reason for it. We don't care about the reason, but this is what it is. It is what it is. And so let's get rid of the fraction, and then we'll have less trouble. So V1 times T2. V1 times T2 will equal T1 times V2. And again, be careful with your subscripts. Don't get them messed up. Because switching subscripts changes it, multiplying to dividing, and it ends up in wrong answers. Now, how do we get T1 by itself?
Divide out the V2.
We divide both sides by V2. These cancel out. And over here, we've got V2. Okay? So now we can rewrite this as T1 equals V1 T2 over V2. So then we plug our numbers in. V1 was, what, 2.8? And use your units, 2.80 liters. T2 was 273 Kelvin. And V2 was 2.57 liters. And we see that the liters cancel out. So yes, I know that. 2.8 times 273 divided by 2.57 equals. So T1 equals 297 Kelvin. No. What? Yeah. Okay. I just, for some reason, my brain suddenly thought I was looking for a volume. Okay, so does that make sense? Let's go back to the problem. We had this at an unknown temperature, and we put it in ice water. The volume went down. Was the initial temperature higher or lower?
Higher.
It was higher because you put it in ice water and it got smaller. So we're expecting a higher temperature, and 297 is higher than 273, so we're on track. Are we done answering what the question asks? No, it wants it in Celsius also. So to get to Celsius, then we have to subtract 273. So we subtract 273, and we get 24 degrees Celsius. So we have two answers, that one and this one. Any questions? What if we didn't convert to Kelvin? What would T2 be in Celsius? It would be 0 degrees Celsius, right? And so what would T1 end up being? 0. Does that work?
No.
No, doesn't work. It just plain does not work when you use Celsius, because the conversion involves adding or subtracting, and it doesn't cancel out. The unit for volume here of liter, if we had milliliters on the top and milliliters on the bottom, or gallons on the top and gallons on the bottom, it doesn't matter because they cancel each other out. But the degrees Celsius and degrees Celsius, math-wise, appear to cancel out, but they don't because of how they're related. All the other units of length and stuff, their relationships, their conversions just involve multiplying or dividing. It's the adding and subtracting that messes it up. Any questions? I like gas laws. I really do.